Ma'am, you're not audible. Ma'am, Subbulakshmi.
Oh, I'm sorry, I'm muted. I didn't notice.
Okay, ma'am. Okay, ma'am. Continue. Thank you.
Started. So what could be the advantage over this binary with binary search in the sense? Yes, of course, we can say like if I want to search or sort any element, I can check it out whether it's greater than or whether it is lesser than. If I'm searching an element which is lesser than the root, then there is no need to visit the right side subtree at all, right? So we can just visit the left side alone. So that is the major advantage. So obviously the time complexity would be the better advantage when we go with BT and BST. So the operations that we are going to do with respect to BST are insert, delete, search, and finding the minimum and the maximum with respect to the tree. So here you can see a simple tree, as I said. So the mid element, which has been, if I want to sort it out, the mid element will be taken and that will be focused as a row. And the left side element would be filled up. So here you can see once the mid is focused, so this is left and the right, which has been in a sorted order. So that's the reason why they are taking us left and right. So as I said, the left would be the lowest one and the right should be the highest one. The highest, the higher value. So here you can see again it's taking 34, 41, 56 would be in the left side, the sorted. From the sorted, they are representing 72, 89, 95. Again, we have to split it out because one data node should be represented in one sec. So then you can see 41 it's been made a root node, then 34, 56. So again, so since this is in the sorted item, it is very easy. So each and every one will be compared with respect to the left and right will be represented. So yeah, what's the rule of it? Any key that we are taking, key of y should be lesser than key of x if y is in the left subtree. Key of y should be greater than the key of x if y should be in the right subtree. That is, the policy is very simple. So that's how the operations, that's how we have made it as a principle and the operations are to carry out. So every element will have a unique key value. Yes, indexing should be different. And the keys in a non-empty left subtree are smaller and right subtree are larger. So this is the second principle. And the left and right subtree are also binary search. It is not like that. Now once I made this one, that alone has to be complete with binary search. No, till the end of the point, till the parent of left and right should also maintain the BST structure, which is the higher should be in the right and the lower should be in the left. And the searching should be leaded to order of logs and log n. Why it's not n? Because we are going on with only the value. If the value is higher, I'm not going to search on the left side at all, right? So that's the reason. And these are all the operations, as I said. So how do we can start? The first one. Here you can see 5, 3, 7, 2, 4, 9. Yes, of course, it follows a binary search tree. It is a binary search tree which satisfies our principle. And given a pointer to the root tree and the key k, okay, which is mean I'm going to search with the key in the tree which is being given. So initially we will start with 5. Return a pointer to node with k if one exists, otherwise return nil. So I'm trying to search a node 3. I want to search it out. If that particular key is not present with respect to the data, then I will be making this as null, right? Then again, the concept is again the same. If it is lesser, left subtree. If it is higher, right subtree. Starting with the root, you have to trace a path till you find a value which is equivalent to k. By comparing with the k value, you have to find out whether this is the current node I'm searching for. Whether, say for example, if I'm trying to search it out with 3, obviously I'll start with 5, right? you will be starting with the root of the tree, which is the pointer will be the root of 3. So that I'll start it from 5. Then I have to keep on moving from 3, 7 likewise. So here you can see another one example. Search for key 13. So the node 13, I have to find it out. So what I have to do? Then 13 in the sense 15 is less than, sorry, 15 is greater than 13, right? Obviously, which side I have to look upon? Left side. So left side, right side, there is no pointer at all. Here you can see there is no key is being presented in the right side. Okay, the time has been reduced. So again, I'm going on with left side. And here you can see the node 6 is being the key now. So 6, again, what is the value? 13. So 6 is lesser than 13, right? So which side I have to look upon? Right side. Then right side I'm going. Right side 7. Then 7 is lesser than 13. Yes, of course. Which side I have to look upon? Right side. Because it is lesser. So the value root is lesser. So I'm going on with and I'm finding. So once the key is being compared and mapped, which is being equal, then you can stop searching and you can move it on. Likewise, if I want to search 14, 14 is not there in the list. So what we will be doing? Again, as right child of 13 is, because if 13, till 13 we have, so 13, if I want to search a number 14 which is greater than 13, obviously it should be in the right side, right? No, for 13 I don't have any right child which is null. So we can stop it and we can say it is not there. So how do I make it present in a code? So data, one is left child, right child. Okay, and it should be presented in a structure. We'll start with the first node. The structure, it will be one and it will pass. So how do I search? The same way. Here you can see 15, which is here less 200 and 500. If I want to search it, so I'll be going on in the left side. Okay, because since 500 it will be in the right side, so 100 we are trying to find it out. Then you can find it out how the searching happens with respect to address. Then if it's not there, it will be represented as null. Here you can see it's represented as null. So the presentation of how the searching happens in BST. So the same way here you can see the code. Okay, in the like the parameter that we have to give us, one is the pointer root, next is the key that we want to search. We all know the root shouldn't be equal to null, right? The root shouldn't be equal to null. If root itself, the number that we are searching, it's equal to key, then we can say the value is being found. Say, for example, if I'm trying to search 15 itself in the, and 15 we all know which is the root and that's been starting point. So 15, then it's find it out and we can stop the searching. Otherwise what we have to do? We have to check whether the data is higher or lower. If the root of data is greater than the key, then obviously you go with left child. If the root of the data is otherwise, else, lesser, then the key is like the data is lesser and the key is higher, then you have to go with the right child and return it. Okay, so this is how the function happens. Until I find the value, till I find the key value, till I search with the visit with all the nodes, you have to you have to just recursive all the recursive this function, and you have to visit all these nodes, compare all the nodes, and find out whether it is left or right or whatever it may be. Okay, so this is how it happens. It's a recursive function. And coming for the complexity, the height, yeah, until the height that we are reaching, we find out. Best is balanced. If it's balanced, then we can say order of log n. If it's a worst case, then order of n. Where we'll have the worst case? When we have only the right side or the left side skewed tree. Okay, kind of skewed tree. So if we have kind of five, which of the following sequence cannot be the sequence of nodes examined? So we just want to imagine it from 1 to 100, how the sequence would be. And they are searching out with 55. And you all know how this center node will be taken. That will be made as the root and the left side, because in the sorted order, we are going to try it out and we are going to structure it. And they are saying which cannot be the sequence of the nodes in the given order. Okay. So this very simple. We have to start off with the sorted order and we can quickly go with the result that's been given. And 10, I'll go with the options. First one 10, then 75. So 10, the right of the 10 will be of 75. And then 75, they have given a 64. So obviously, which is lesser. So 64. Then 43, again 43 they have given. Again 60 they have given. And then which is higher. And again 57, which is lower. So 57. Then 57, 55. So this is how they have given. This is the which of the following sequence cannot be the sequence. That's the question they have asked. 90, 12, and 68, 34, 62, 45, 55. So this is also one possible. And then you can see the next option is 9, 85, which is greater, 47, lower, 68, higher, and 43, lower. Okay, next is 57, next is 55. Okay, how this cannot be possible? Because 43, I cannot be posted in the right side of subtree, right? So 47, since you have already 47, which has been revisited. Okay, so not possible. 43 cannot be in the right subtree of 47, right? Because this holds a right subtree. When I have this 47 to 43, what will happen? In the right side should be greater, no? And the principle of BST is being collapsed, right? So 43 cannot be visited after seeing 68 in the right side of 47. Since we have already, if 47 is not there, then this sequence is also right. But then if 47 is there, which is already there, which is higher than lower than 68, but then again, I cannot place a value which is lower than 47. Okay. Same way, D also you can able to check it, and D is fine. You can see 79, 14 should be in the left, and the right of 14 should be 72, and the left of thing will be 56. Okay, likewise, you can just go on and you can check it. Okay, so these sequence cannot be made it as BST sequence. And yeah, as I said, we'll discuss all the operations. The first operation is inserting key 35, which is being tree is being given, and you have to insert 35. So it's very simple. So 20, 35, 35 is greater than 20. So obviously we will be going with right side, right? So the right side, what is the, which position we have? So this position, this address we have, which is of 35. Again, the right side, we have to insert it 35. Okay. And inserting 13. If I want to insert 13, and again, this is the root. Okay. Yeah. In the root, the key value is greater than root. So obviously, I have to go with the right side of the tree. So go with the right side. And again, you have a value of 18. Okay. So 18, which is greater than 13. Okay. And then you have to trace a path, because we have to place a key value 13 in the right place, right? So again, this 18, we are going to compare it with, because if the key value is greater than 18, then I'll go with the right side. Since the key value is lesser than 18, I'm going with the left side of the 18. So 15, again, from 15, you have to find out the left side, because 15 is greater than 13, and you have to place a node 13 in the left side. Okay, so this is how you have to find, and this is the code snippet of it. So here you can see, and the parameters that I have to go inside the insert function is root and the key. Again, we have to check on for the null condition. Okay, and here we are going to insert. So for that, you have to create a new node, and you have to find out the size of the node. That size of the node along with the pointer that has to be inserted. That's what here it's being done. If new node is null, okay, which means I could not find a space, then it is called as out of space. Okay, else new node data, which is key. That is the key that we are assigning the data of the new node to the key. the key which been assigned to the new node of the key, and the left side, right side, whether I'm trying to like find out the key value. If it is equal, then it is called as null, otherwise return. Else we have to insert it. So here again, you have to find out the left side and right side, which should be lesser than or higher than. So left side and right side. Root of left side is key. If the key value was lower, then obviously I'll go with the left child, right? Left child, and the key will be inserted. Insert root of left child comma key. Otherwise, if it is higher, then I'll go with the right side. Then the right side, what else I need? The key value to be inserted. And what is the root? See, in the last example, we have seen, no, this 13 has been inserted to the parent is a child of parent 15. And what's the root? The root of 12. So that's what is being calculated. Else key is there in the tree already, do nothing, because we have to check already the same number is being there or not. So that's also most important. So all these three sections we have to write in when we are coding it. And coming for the shapes, so shapes again degenerative. If the skew tree is being presented and you are trying to process it, then that is called as degenerative, and it will take the entire height because I don't have an option of right left. So I'll go till the end. So how much time complexity it takes? Order of n heights. How many nodes I have, how many height or depth I will have, till that the complexity arises. Okay. So this is the insertion and insertion operation and this shape with respect to BST institute. And finding the minimum and maximum, minimum key value and maximum key value in the given node. Sorry, in the given tree. So the minimum obviously would be in the left side. So left side would be searched, and the maximum is located at the right node. Okay. And what about the complexity? Find minimum and find maximum. So which will have to visit all the nodes of the left and right so that I can come up a conclusion of finding minimum and maximum. Right? So here you can see the pseudocode. So pointer node, if it's minimum, then left child. If it's not null, then make that as root of left child. If it is maximum, make sure it's not null again. Then find out the root with respect to the right child. Okay. So here you can see this is the minimum and this is the maximum of particular. Yeah, predecessor and successor. So here we are going to find out nodes left subtree next to smaller node, not the entire tree, the smallest node, not the entire tree as we have seen in the minimum or maximum. So here what we are trying to find it out. So what's the next predecessor of that particular node, which means the next smaller one that can be done in the left side, and successor next large node in the right subtree. Okay, here you can see a tree is being given, and if x is 2 children, its predecessor is the maximum value in its left subtree, because x has 2 children, predecessor is nothing but, so next smaller node in the left subtree. Okay, so that should be the maximum value in the left subtree, and the successor is minimum value in the right subtree. In the right side till the down, you are trying to find out what is the minimum value that's been presented in the right side, opposite of minimum max. Okay. So successor of a node in a tree, assuming all keys are distinct, assume all keys are distinct. Okay. And next smaller node in nodes left question, I'm trying to find it out. So this is nodes left question. Okay. So from 10, you have a section of 5. From 5, you have till to 9. And from 9, you have a left side portion of, okay, left of 9. If the pointer is, so we are assuming, because we are going to find out, trying to find it out, like what is the next smaller node. So obviously it will be in the left side. Left shouldn't be null. Okay. If it's equal to null, then we have to return it null. Else what we have to do? Maximum of node left child. Okay. What's the maximum value? From 5 to 9, 7. So from 10, what is the maximum that I can get with left side of tree? What is the maximum value? 9. Same way, successor in the sense, the right side, what's the minimum value that I can get? Okay, here you can see 20, 17, 15, 10, 15, sorry, 20, 17, 30, 15. So obviously 15 should be the minimum. Okay, and next minimum 15 to 17. This is how. And here you can see the code return minimum of nodes right child. Okay, so the same example is being given. If a node doesn't have a left child, then what you will do? How you will be able to find it out the ancestor or like first left? So if the right subtree of a node X in the BST is empty and X is a successor Y, then Y is the lowest ancestor of X whose left child is also an ancestor. Because I don't have a left child, I don't have or else if I don't have a right child, how I can able to find it out? So here you can see it's a kind of like left side I can have. Okay. So from this you will take, because the left child you have, so producer you can able to find it out. Say for example, if I don't have a right side at all, then how I will be able to find it out? So here you can see another one example. If the right subtree of the node X in the BSC is empty, the right subtree is totally empty, okay, and X has a successor Y, yes, you have, then Y is the lowest ancestor of X whose left child is also an X. So we are considering this part, and from this part you are making that as an ancestor and you are trying to find it out. This is right child is not at all there. Both are there. If it's this is the successor of X, then right side. To make this as a for finding the ancestor, this is how you have it. Okay, and these are all some workout samples of how you can able to find it out the node producer ancestors. Then the final operation is delete. Delete is very simple because everything is being ordered here. Element, final element is being in the leaf, okay, in a degree 1 node, element in a degree 2 node. These are all the cases. One thing I can go on with the leaf node, or else I can go on with respective degree, right? So here node Z, assume node Z you are trying to delete, which is not having any children, which means it's the leaf. Okay, delete Z by making the parent of Z point to null. Because that is presently pointing to null because it doesn't have any children, it's the leaf node. Okay. To delete the current pointer, assume this is the current pointer, then what you have to do? From the left side, you have to delete a node which is equal to Q, a key, and that's been pointed to null, right? So here you can see current is equal to current, fine, if it's greater than left child. Then you can go for delete operation. If it is higher than, then you have to go with right child and you have to go with delete operation. Case 2, delete a degree 1 node. If any of the node, if you are trying to delete a node which is having 1 children, okay. So what you have to do? You have to make a parent for this. Say for example, delete key 40. Okay, delete key 40. So 40 is having one side, right side is it's not having any children, but in the left side it is having children. And this has to be moved on to another parent, which 40 pointer, which the pointer of 40 is holding to the root, right? So the root of this or the parent of this has to be transfer the entire leftover children to the top, right? So delete Z by making the parent of Z to point Z child instead of directly deleting it to Z. And then if I want to delete key 15, which is in between it, okay. 15, because 15 is having a child 18, but then 15 is having a parent too. So what should I do? I should be able to link this pointer to the root of this, parent of this 15. So this is how it works. And if it's degree 2 node, degree 2 in the sense, if it is having 2 child, okay. So 10, assume if we want to delete 10, you can see 10 is having 2 children, which is of 6 and 15. Okay, if I want to delete it, then what would be the case? Here you can see replace either producer 8 or successor 10. Because here I can see if I want to delete it, replace with the largest key in the left subtree or the smallest tree in the right subtree. Anything is fine. Both the cases will work. Both the principles are fine. If I want to delete a node, then I should go with the largest key in the left subtree. Okay. So in the left subtree, the largest and or the smallest is the right subtree. What is the right subtree of this one? 8 and 7, right? So this is the right side. So this one I can either make, or I can go with 50. Okay, and again, because in the right of 10, I have 50. So how should I able to delete it? So here you can see I'm deleting this. So obviously 8, the right of 6, because I have a connection of 10 to 6 and 10 to 15. Either I can go with 18 or with 8. So if I'm going with 8, then 8 will be the top, and then I have to finish off the connection, and then I should make sure the BSc principle is being followed. Okay, the left should be lower and the right should be higher. That's the reason why they said higher and left. Lower value to you have to go pick off the value which is higher in the left subtree, which is actually higher in the right subtree, which is 18. Then I'm making 18. Because what's the total higher value? Because I should follow the principle of BST. The left should be lower. So unless I make or unless I choose the topmost value in the left subtree, I cannot satisfy the principle of BST when I'm deleting the root node, right? So here you can see 18 is being shifted. So the rest is being followed. So the lesser value will be of, all the values will be lesser, and the right side, all the values will be greater. And this is the algorithm for deletion and BST. So first case, as we have discussed, has two empty subtrees, which is not having anything. The parent is null, then it's very easy. If it's having a left and the right subtree, okay, place the node value with the maximum value in the left subtree. Delete the maximum node in the left subtree and make it as that parent, delete it. That's how it works. And what's the case 3? If it is has no right child, sorry, no left child, what we have to do, left child is not there. And if we want to delete, then the link the parent of the node to the right. Okay. Because we don't have any left child, so we can, since we are deleting the parent, we can make the right child as parent and we can move on it. If the node has no right child in the sense, link the parent of the target to the left. The same way, the reverse, vice versa. Okay. So deletion pseudocode. So it's in detail. So the parameter, the root, and the key. Okay. So next we are going on with we are trying to search it because we should make sure the key, what we are trying to find it out, delete it, it's already found in the tree. Otherwise, it's not possible. If current is not equal to null, then we are making that as a current node. Here you can see searching of key. It's a current node. If it is we are trying to find it out left side or right side. So child, if current of left child is equal to null, then we have to move into the right child and free of delete. We are just calling the function and it's deleting it. Else, if it's right child, then go with free of delete to the right child. Then same way. And in the last case, if it has 2 children, then if it's 2 children, then what we have to do? We have to make the left side top, the left side highest value at the top. That's the reason why successor of data would be the current value that will be moved to the parent. Okay. And coming for the in-order traversal of BST, as we have seen in the binary tree in-order traversal, so everything will be in the sorted order, 15, 6, everything will be there. So print all the keys in the sorted order. That's how. 2, 3, 4, 6. Likewise, the in-order traversal of BST would happens. Since the left side would be the lowest and right side would be the highest, the entire order should be, if it's an in order, we have to make it as in the sorted order. So in BST, we know the last one, the last value, the last leaf value, which was pointed to null. We are emptifying. We are just actually wasting the space of it, right? We don't have any connection because 4 is being connected to 3 and 3 is being connected to 6. Yeah, of course there is a connection, but then we are making, since there is no child, since that's a leaf node, we are emptying or we are wasting the space of it. That's how the next concept comes into picture, which is called as threaded binary tree or threaded tree. Okay, it is having a lot of wasted space. The leaf nodes have 2 null pointers because in binary we have 2 sides. So 2 null pointers, it is wasting. So here you can see how many spaces, how many null pointers is being wasted in a simple 10 or 12 sets of nodes. Okay. So these pointers has to be used in order traversal. Okay, that's the concept of threaded tree. So threaded tree, which will just do how it will overcome the wastage phase node. It will just have the pointer reference to the next node in the in-order traversal. So in-order traversal is nothing but we are just writing it in the sorted order, right? If a pointer is actually having a link or a thread, we have to keep a boolean for each pointer. So we are ultimately trying to just focus on the space wastage. Okay, here you can see. Assume this is a tree. So 1 to 3 because it's having a connection. 5 to 6, 7 to 8, 9 to 1 because obviously this is how we are going to write the sorted order, right? So 1 to 3, 5 to 6, 7 to 8, 9 to 11. Okay. So obviously we are not wasting any space at all. Here we are not wasting space in 1, 5, 7, 9 at all. So how should I have to do? So here you can see 1 to 3 and then the output would be of 5 to 6, 7 to 8, 9 to 11 and finally since this is the last node which will be of 13. So where we will be implementing it? When we are transferring or when we are traversing it to the in order. So that time just to reduce the wastage space of it, it will get reduced. And coming for the best time comparison, how does it happens and all. So what's the best case in a tree, worst case in a tree in the BST operations? In the BST operations, it would be of log n. Okay, all the BST operations will be in the depth of the tree, which would order of D, if it in the worst case, and the best case would be of log. So in the worst case running time, we have to visit all the nodes, which is of order of n. When you insert elements in ascending order, say for example, 2, 4, 6, 8, 10, 12, okay, into an empty BST, what we have to do? If it is in the sorted order, then the balancing is most difficult because we have to maintain the principle of BST. That's most important. We have to make sure all the left side subtree or this or lesser than the root, right? When it's in the sorted order, we have to revisit all the elements. We have to check out all the elements and we have to place it. So obviously the time taken would be high. So that's what unbalanced degenerated tree. I can go with left side or I can go with right side. It depends on the value that's being given. So that's how you have to make it. So it will, here you can see unbalanced BST. 1, 2, 3, 4, 5, 6, 7. Okay, since it is higher, all these have been put together. Okay, here you can see 2, 5, and there is no child for 5 and all. And here 2, 1, 3, and 5. Here you can see all these are kind of like unbalanced because we are just, this is unbalanced, but we are trying to make it as balanced. We should visit all the nodes and we have to make them balanced. That's the reason why it is taking order of big N times. Okay, so how we can able to approach it, how we can able to balance it. So we have to balance it. Without balancing, we cannot say the BSE will result out in a better complexity. We have to adjust it. We have to check out each and every nodes. Maybe some nodes will go with very deep. Maybe like some nodes has to be revisited. So all these are most important. So that's where the third one, which comes in called as ADT. Okay, so the height will be balanced. Here the most focus on height balanced, or else play trees were there, B trees. All these are for balancing the binary tree. These three comes up. So first one is ABL, next is play and B. So coming for the perfect balanced tree. Okay, here you can see, this is an example given. Okay, if I want to make it as complete tree, actual full complete tree, then insert 2 in the tree on the left hand and then rebuild as a complete tree. So it's asking to insert 2. So where I'll be inserting? In the left side, right? So in the left side, you will be inserting. And you all know, like again, we have to check, go with the left side value, right side value, higher, and everything has to be checked. Okay. So here you can see, once I'm trying to insert it, the root has to be checked because I'm trying to insert a value. If I want to make it as complete tree, if it's not complete, if it's just a full, then I can directly insert 2 and I can make it as 4, then 5. Then in the right side, I can directly write as 5. and this will be of 9, 8. If I want to complete in the sense, everything should have a left and right. No. So that's what it's being made. The modifications has been made. Okay. Able is good, but not perfect balance because height of left sub-tree minus height of right sub-tree, it's a balance factor which is being calculated. For every node, height of right and height of left by no more, it can differ more than 1. So this is the rule which we have to maintain it. So minimum number of nodes in an able tree of height h is n of h. So minimum it can have, because I should maintain a difference of 1 node. Okay. If it's 1 node, then node of n of 0 is the first one. The minimum number of nodes is 1 because it's 0. And if it's a minimum value height is 1, then the value is 2. Okay, here you can see it is of 1 and 2. Okay, if it's I have only root node, then that will be the number of nodes will be the 1, then the height will be 1. Okay. Sorry, height will be 0. And then n of h is equal to n of h minus 1, n of h minus 2 plus 1. So likewise, the minimum number of nodes, if I want to calculate, this will keeps on going till I have the value. Okay. And here you can see the height of the able tree. All these are some, how we are trying to find it out. If we have n nodes and the height h, how with the help of Fibonacci analysis, which is being calculated. Because they were taking n of h as the minimum value. If it is minimum, then how we are trying to relatively balance it. That's what they have given. And node height here you can see this is 6, 4, 9, 1, 5. This is the node because we have to check on the balance factor, which should not be more than 1, right? So here you have to check on the height is 2, 1, 2. So 0, 1, and 2. I have height is 2. Okay, the balance factor, I'm trying to find it out. 2, 1, 0, which is 2 minus 1, 1. Okay, so that's how you have to find it out. Here you can see height of left minus height of right. So find it out. So which is 0, 1, 1. So here obviously it will be of 0 because this is the last level. And here I have 2 empty height, which is of 2. Okay, and node height after inserting 7. If I'm trying to insert 7, then again it's very simple. Same way, once you are inserting or you're doing single rotation, double rotation everywhere, you have to make sure the balance factor is maintained. Okay, if the balance factor is maintained, then you can say ABL. Otherwise, you can say here you can see the balance factor, but then here you can see the balance factor which is being maintained. So it is ABL, and here they are saying it is a strong ABL. All these are explanations. And insert and rotation happens. How does this happens? May cause balance factor to 2 or more than or minus 2. Only nodes on the path from insertion point to root node have possibly changed in height. Okay, while trying to insert. So after the insert, go back up to the root node by node, updating the heights. Okay, and do the difference of h left, right, and do the rotation again, and go with the adjustment. Adjust the tree and make sure you are going on with 2 or minus 2. Okay, single rotation. How does single rotation happens? Because since it's of 2 and 1, and they have made with the single rotation, they have made it as 1 and 0. Okay, because 7 has to be made as a perfect balanced tree, and the 7 is being made in the left, and the 9 is being made in the right, and 8 is being made in the root, so that the height of that balanced tree, ABL tree, is being balanced. Okay, so these are all the insertion cases which we have seen in the example. If it's outside case, so here you can see this is a height, and these are all the nodes, and these are all the leaves which has been presented. Inserting into X destroys the ABL property at node G. If I'm trying to insert it, the height would be, if I want to insert into X, if I'm trying to insert it, then obviously the height will be higher, right? But then here the height will be different. So the ABL property will be pulled out. Then what I have to do? I have to do a rotation so that I can make it balanced here, so that here and here I can make it balanced. Here you can see. So making it as a rotation of K and J and changing the outside case. So they have made this K into root and J to down. So J is being made down, and here also H. And the H is being, right side rotation is done. Okay. And the all the ABL properties has been changed. And here consider valid ABL subtree. So this is valid because all these are H equalized. And inserting into Y, what will happen? Again, H plus 1 will increase. Again, I have to do right side balance. So K will be the root, J, and again I will have to come up. So that's how the structure of each and everything while inserting will be made. And yeah, so node I and subtrees V and W. Okay, so Y node will have, and if I want to insert it, what I have to do, again, the left side double rotation, because single rotation is not enough. You have to insert I with respect to V and W, you have to insert it. So that's the reason why they are doing this double rotation for the first rotation, and for the second rotation, they'll be doing this. And now again, finally, a final right rotation, complete the balance, which will be transferred. So it's again very simple. So they are rotating it in a single way from K to I, K to J. So here you can see K to I is being changed, and K to J, the left rotation has to be, has been completed, and the right has to be happened. And I to J has to be completed. From I to J, I have to do the second round of rotation to make it as complete. And this is the balance factors. Okay, so the left and right will be balanced in the during the implementation. So this is again the implementation point. So it will have the reference pointers. If it is right, left, okay, then how the rotation happens. Modify the heights or the balance factor of N and P. So every time when I'm doing rotation, the N and P of the balance factors and the heights would be changed, and that should be maintained when I'm trying to change it. Double rotation, how I can make it in a two lines. So double rotate from right, reference node pointer. So here you can see, if I want to make it as complete, so I should do double rotation. So here you can see that, so that has to be come here, and here the nodes has to be placed in the left side, and it should go. So that's how the double rotation happens. Okay, so here again, just the insert pseudocode. Okay, make sure you are maintaining the balance and you're not duplicating anything. Okay, and duplicating in the sense the function that we are trying to call it out, what to say, I mean, each and every balance factor maintenance you can have, you can go revisit it, and you will be checking it whether left or right rotation. Okay, so again, this is an example. So an example of insertions in an AVL tree, insert 5 and 40. So you can see the height of it. Okay, here it's been balanced 2, 1, and 0. So which is being calculated. An example of, and they have given insert 5, 40, right? So 5, obviously I'll be inserting here. Okay, and 40 is the highest value, so I'll be inserting it here. Okay, so now I'm trying to insert 45 into this, where I'll be inserting. So inserting 45 will lead to the right of 45, right? For every step, you have to calculate the balance, the height and the balance factor has to be calculated. And inserting 34 again, the left of it. So because 35 we have, so the left will be of 35. Why I'm not going right side? Because it's of 20. So I am, why I'm not going left side? Because the root is 20, so we cannot go it. And the same way here also you can see, which is being balanced and weight. So how I can able to delete it? So again, for deleting, you have to make sure it's being balanced, order of login. Okay, search and insertion deletion can happen login, because we are going with the left or right alone. Okay, so here double rotation solution. If I want to make it as in a single way, then we have to pass out the reference pointer, whether we are rotating it from left or whether we are rotating it from right. Okay, then we have to pass on the pointer to it, because it starts from rotate from right. That should be given to the left, because here I have to start here and I have to bring it out this place, right, to make it as balanced. And yeah, this is the concept of AVL. So AVL works better, the rotation happens, and what is the pointer space wasted in the BST is being used in a better way in the threaded tree, and AVL is the balanced solution that we can give with the help of AVL. And finally, I will conclude with this heap. Heap, again, it's very simple. So heap, again, we are going to check on with all these nodes. Okay, so heap is nothing but the complete, or you can say it's a useful data structure when it's necessary to repeatedly move the object with the highest priority or the lowest priority. Or I can say when you want to do insertions, need to be interpressed with removals of the root node. If I want to remove it and I want to check on with the priority, I have to do it. So this kind of data structure, if you want to have in your application or the program, then you can move on a structure called as heap data structure. Okay. So repeatedly, I can able to remove the object with the priority of highest and lowest. If I want to insert it, then again, I have to go on the removal way, and I can able to, if you want, you can go it in this way. Okay. So these are all the topics that we are going to discuss. Okay. So as I said, consider the highest element or the lowest element from the list. So with the priority. And reason is the time complexity is, of course, we are going on the time complexity because the most important thing is they have to reduce the time complexity which is being processed in every data structure. Okay. A group of things lying on one another, a heap of stone. You can see a heap of stone or a pebble. If you are trying to construct it, if you are trying to like stack it, how will be making it as? So in the down will be the base will be more higher, and you keep on adding stones to it or pebbles to it likewise. In data structure, how we'll be having in data structure, all those pebbles or the stones will be referred to as elements. Okay. So we have to structure all these elements in a particular order, and then once the order is done, you have to process it. Very simple. This is how heap works. So it's a complete binary tree. So each value corresponds to value, and that needs to be stored. And it's completely filled up to the last level because since it's complete binary tree, so the last level till last level, and specific order is being maintained because, as I said in the last slide, an order will be maintained. Since we are stacking of some stones or heaping of some stones. So types of heap, maximum and minimum. So here you can give an exercise how the complete binary tree is filled with a heap structure. So this is one exercise you can give it to students. And maximum in the sense here, maximum and minimum. If the node parent is greater than node child, then you can say the property that heap structure is maximum heap. Parent is higher, the child is lesser. Okay, or it can be greater than or equal to the value of the child, no? Then that's called as maximum. I'll show you example. So here you can see the parent is higher, the child has the lower value. So these are all the maximum heap. And if it's a minimum heap, then minimum in the sense, obviously no child should be the greater value, the parent should holds the symbol value, minimum value than the child. So this is one example wherein the parent holds the minimum value. Okay. Here you can see a mixture of all these has been given. So this is minimum, and this is again minimum, this is max, and this is minimum, this is max, and this is max. So we can ask the students to, since we are heaping it up, we can ask the students to how we are trying to show the alphabets in the maximum heap and minimum heap. Suppose any choice of alphabets or the entire alphabets which is being given to you, how they are trying to heap it off. So this is a kind of simple students, because a simple question which can be asked to the students, because we are just asking them to represent it, not we are asking to calculate it or something, right? So representation already using list, the same way we are trying to represent it, but array we are trying to represent. Why? In the sense it will be very simple. So that's efficient and easy access. Here in the example, they have been given in the array representation. So root of the first tree will be the first question. That's the first index. To compute the parent of the given index, then the select floor I by 2, which we have seen in the previous examples, the same way since it is of array. To compute the left child, again, you have to left is 2 into I. And if I want to find out the right, 2 into I plus 1, which we have already discussed in detail in PS binary tree itself. So how I can able to representation of maximum heap as binary tree and corresponding array. So maximum in the sense the root is maximum, right? So here you can see how I can able to represent it. So 1, 2, 3, 4, 5, 6 index starts at 1. So I have to represent this 30, 25, 10. So this is one level. Then 20, 18, 85. So this is how the representation happens. So how does we have to calculate it? So from the array representation, how does I can able to find it out whether it's left side or right side? So it's very simple. You can go on with the formula 2 into I or 2 into I plus 1. 2 into I plus 1 is the right and 2 into I is the left, right? So here you can see 1, which is 1 into 2, 2 into I is the 1, okay, which is 2. So at index 2, you can find the left of the root, which is 30. Yes, I'm finding it, right? So 2 into I, which is 2, I'm finding it. 2 into I plus 1, which is 1 into 2, I is 1, 1 into 2, which is 2, 2 plus 1, which is 3. So in the third question, I should be able to find out the right of this index. Then, if I want to find out the right of this index, then what I'll do? 2 into 2, which is 4, right? The left of index, the left of E2. So 4, what is the fourth location? Fourth location, I'm having a value 20. I can able to find out the left side of the tree, left side of the heap, which is 20. So this is how the representation works. So from the array representation or from the list, if you want to try to find out the constructed tree or the portionize the tree, then this is how you have to calculate it. Here you can see for all the questions I have given the with respect to arrow, I have given mark you. Basic operations again, insertion, deletion, sorting, and finding out since we are going on with maximum or minimum value, how we can do insertion, deletion, sorting, and all these two. So in maximum heap insertion, we have to fulfill the property to complete a binary tree. That point, we have to make sure whatever the operation that we are doing, we have to make sure it should be of complete. And insert node have following the steps. So insert node, again, at the leftmost last level of the tree, we are going to insert it. Okay, because it is of maximum heap. And the insertion of element check maximum heap property, parent should be greater than child node. If satisfied, then insertion done. Otherwise, we have to swap it. We have to swap the parent node, and then insert the node. This process continues until the maximum heap property or no node left for comparison. Till that, we have to find out. So these three are the cases we have to make sure we are coding. In coding, we are adding it. So we have to add 35. And it's a complete binary tree. The node will be added as leaf node. And this is the same binary tree I'm taking. And the max heap. And they are adding 35. Max heap in the sense the root should be higher. So obviously we need to should do some kind of swapping. So first initially it's adding 35 in the left of 20. And then, okay. So, and then the structure happens. And then what I have to do? I should able to swap it, right? Because maximum heap property is not maintained in the previous one. You can see. 8 is the index for 35. Okay. And here 8 by 2 is 4. So we have to bring into fourth location, fourth index. So that's what here they are doing. Here you can see. So till 4 with the 20, they are trying to replace it. And once replaced, here you can see 35 is being brought into the 20th position. And 20 is being brought into the 35th position, which is the 8th position. Okay, so this is how it's being swapped. And the same way, after swapping also the heap property is not satisfied, then again we have to check in what we have to do. Now the question is already 4. So 4 by 2, which is 2, I have to swap in with second position. So what's there in the second position, we have to check on, which is 25. So with 25, here you can see the question 25, the question second, it's holding the data of 25. Node 25 has to be swapped with the 35 because we have to maintain the heap property. Okay, simple, very simple. So again, we are doing. But then still the heap property is not maintained. It's not satisfied. So again, we are finding the floor value, which is 2 by 2 is equal to 1. Then again, we are swapping it with the first one. Here you can see the value, the 30, the first question will be replaced with 35. So the second will be replaced with first. So here you can see it's been replaced and the structure is being updated. So for every replace, you have to update the array structure you have. So the same thing here, it's been given. If it's greater than 1, then go check current, compare with the node. If it's higher, if the parent is lower, that's what I meant. If the key is higher, if the parent is lower, then you have to swap it. Then you have to find out, then return it. Okay, so this is how you have to check on. Then the same way, insert 80 in the following max heap and show the result. So again, 80. This is again max heap, so I'll just skip. If you want, you can once you're free, you can just do it. And deletion, how does deletion happens? Deletion again, only at the root node. That's the principle here. So only at the root node, the deletion happens. Replace the root node with the last element. Okay, it will be replaced. The last leaf node will be inserted at the root node. Okay, because we have to complete the binary property since we are deleting starts from the root. Okay, and check maximum heap property by comparing the parent with the child node. Compare both the child nodes if it's available. Okay, if both the child nodes were available and if you're deleting it, then you have to compare it. Whoever node is greater, it will be compared to the root and that will be swapped. Okay, likewise, because we have to make sure the property of the heap is being maintained. That's it. Again, whatever operations we do, the same kind of comparison we have to do, and we have to make sure the principle of each and every tree property is being maintained. That's it. And only the structure we have to check on, and when we are coding it, we have to make sure all the parameters that we want, it's been given inside the function that you have. Deletion process will delete 40. As I said, the root starts from root. Complete binary node will add as a leaf node. So the leaf has to brought in front. Okay. So what's the last leaf node, which is of 4. So here you can see the 4 will given to the top. 4. Again, the condition is not, the heap property is not being satisfied, right? Since it is of maximum heap, they say. So what they have to do? They have to shift the last node till it solves the property and then delete it. So here you can see, if I want to delete it, I'll be bringing it to the top, and you can see that's been swapped with the root node, and next it has to be followed. So since this again doesn't satisfy the heap property, as I said, we have to compare with the child node of it. Next, what's the second step? So first step is deleting the root node, and the second step is we need to swap it. If the heap property is not satisfied, we need to swap whatever the leaf that we brought into the top, that has to be swapped. Okay. So again, the higher greater will be compared and the greater one will be swapped. So again, you can see 25 and 10. It's a child node and that's been swapped. Okay, 25 has to swap and that has to be brand because that is a higher value. That's it. Here you can see 25 will come to the top, 4 will come here, and 10 will be swapped here. So the same way, again, we have to check whether it's been comparison has to be made with 20 and 18. Okay, 20 will be compared 4 and 4 and 20 will be finally swapped because 4 is minimal. Okay, that has to be compared and that has to be removed. The same way it is happening. Here you can see. And finally, 15 will be compared with 4 because we have this, we need to bring 4 to the end of here, right? After deleting it. So 4 and 15 will be swapped and it will be bottom. 15 will be in the up, which means the right of 20, the 15 has to come. So that's how it comes. The final tree will be as follows after the first deletion. So the first deletion is being done with the root node. So this is how the first deletion happens. Okay. And this is how the deletion happens. Again, I'm saying the first root node and then you're trying to bring out the last leaf node to the top. Then you're checking whether the heap property is being maintained, max or min accordingly. If it is maintained, then no issue. If it's not maintained, then again, you have to check out the child of it, the left and right. Who's the highest value that you have to bring it to the top. Till you reach the final, till you reach the actual property of it, then you have to do the scan and you have to swap it. Then heap sort is again a sorting method. So you have to sort it. So if it's a max heap, then like create a max heap, delete the element from max heap one by one from the array. I'll show an example how to delete and how to sort it. So this is the array elements 20, 25, 2, 3, 5. So this has to be sorted, of course. So 20. Okay. So 20 will be in the top. 25, that has to be replaced. So it's being replaced. Oh, sorry, swapped. And then 25, 20, because it's max heap, so it's coming at the top. all the rest of the rows because we have 2. And then that 2, we have to place 3. And then we have to place 45, right? So here you can see 25, 22, and then the left of it. We are just going with the left side and right side order. That's it. Once we are done with the first level, this level is done. Next, we are going with the second level and we are trying to find it. So where the 45 will come? Of course, in the right of 20. Okay, so this needs to swap because 45 is higher. So obviously this needs to swap. Here you can see the swapping is done. And then again, we are not yet done, right? Because 45 is the higher and it's there as a child. This has to be shift. That's the swap which happened 45, 25, 2. Okay. And finally, in the once heap is sort, if you want to delete it one by one, first element to be deleted is the root, which is 45. So here you can see. Next, with the position, you can able to once I'm deleting the 42, what I have to bring? I have to bring the last leaf node. What's the last leaf node? Fifth node, fifth index node has to be brought to the top, and 25 to again we have to do place the elements because 20 is lesser than 25, which has to brought to top and swap with 2. So here you can see after deletion, I'm getting 25, 22. So now the 25 will be deleted. So the elements will shift forward by 1 emptying the second last position because the second last position, the element will have already been deleted. Okay. So 25. So finally, I'm bringing it 30, 22. So here you can see the position of 4 and 5 has been changed from 25, 45 has been changed. And then the max heap again by comparing the first child, then swap with the parent. Okay, here you can see swapping with the parent because it's lesser. So here you can see it's being swapped and 20 is being top and 3 end. So this is how it keeps on go. So element 20 is being deleted. The next element. So already we are done with 45, 25 and 20 has to be deleted next. Next 3, next 2. This is how the element is being deleted. So likewise, it keeps on going. So 20 is being deleted and 2 and 3 we have finally. Then 2 and 3, 3 we have to bring into top because 3 is greater than 2. And then finally, after doing this, here you can see, after swapping this, we have only 2. That 2 is the first element which we can delete. Okay, so this is a kind of exercise wherein we can sort. So finally, we have the sorted list in this order 1, 2, 3, 4, 5, 2, 3, 20, 25, and 45. The time complexity is -n because the insertion, how we are happening is insertion of each and every element, n log n, and insertion worst case, average case, best case is the most important. Worst case is like if I'm going on with all the elements, our average is same. Okay, best case because we need n log n steps to go with all the elements because you can easily see in insertion how we try to insertion because we have to check with maximum and minimum heat property and we have to compare with all the values. Swapping has to be done. Okay, whether it's in the subtree of whatever it may be. So total time complexity for all the elements to be inserted is 2n log n. Okay, that is you can find. And can we reduce time complexity? Yes, there is another method called as heapify method. So maximum heat property will be satisfied. Heapify method will be applied this method on the leaf node. So leaf node only you're going to apply it, and the leaf node which will be indexed by n by 2 plus 1 to n. If the index starts from 0, then you have to check on. So this is one, but this is not there in your syllabus. Just for knowing, I have given this. So heapify method you can do and you can compare it. Yeah. So that's it. Thank you so much for your patient listening.
Thank you so much, Lakshmi ma'am. So it was really useful. We were able to know more about threaded trees and all. Participants, if you have any doubts, you can ask Subbulakshmi ma'am. I hope they don't have any doubts, ma'am. Thank you so much for spending your precious time with us, ma'am.
Thank you so much for the invite, ma'am.
Thank you, ma'am.
Thank you. Thank you so much.
Thank
Shall
you.
I leave the call?
Yeah, sure, ma'am.
Okay.
Ma'am, 1 month, ma'am, I'll take wait on a video session. Participants, I kindly request you to switch on your videos for taking a photo. Thank you, participants. You can leave for the session and you can join by 1:15 for the third session. Thank you.